and thank you for the introduction. So I'll talk on non-proportionality measures for multi-axial fatigue loadings. It means I have a particular loading, multi-axial loading, and I want to have a number which says me how much non-proportional this loading is. So, I start with an introduction, then I tell something about the classification, and then present measures which are based on the motion inertia tensor, then a measure which is based on the motion correlation between two signals, and then the measure due to Kanazawa and the multi-axiality factor whose in multi-modified by Susmov. And then some questions will arise. Okay, so the setting is we want to do some evaluation of fatigue life using simple stress-based methods, so it's high cycle fatigue. And for some materials, the non-proportional loading results in a shorter fatigue life. And most of the conventional stress-based hypotheses do not take this behavior into account. And so we need some explicit evaluation of non-proportionality. Okay, so let's see how it should work, presumably. So there are some local stress components, and then in each plane some normal and shear stress components can be computed. And these are they used as input into fatigue life hypothesis, and then fatigue life estimation occurs. But as I told previously, in case of non-proportional loadings, the usual hypothesis will be much too non-conservative. So there is one more step which evaluates the non-proportionality. Okay. So there are a couple of measures which are going to be discussed. They can be classified similar to the fatigue life hypothesis into integral measures and into critical plane-based measures. Integral means stress values are integrated over all planes, or stress tensor components are integrated over time, or both. And critical plane means critical plane is identified, and stress values related to this critical plane are used in order to produce a non-proportionality evaluation. And the application, so because non-proportionality is something about how the shear stress amplitudes are distributed over different planes and over different directions in a certain plane. So it's proposed to take some shear stress amplitude, which is involved in a particular hypothesis, and modify it using the non-proportionality factor and the material parameter, which has to be determined in some way. Okay. So now I start with the non-proportionality measures which are using moment of inertia tensor, and some general notions I need to introduce. So this is the usual shape of the stress tensor, and in order to apply the measures, it's transformed into vector with 6 components, and the shear stress components are weighted with the square root of 2. And this is used in order to obtain this identity. So, and this identity means finally that the measures which are going to be discussed are independent of the choice of the coordinate system. It doesn't matter how you rotate your coordinate system and in which coordinate system you write your tensor components, the measures will yield the same result. Okay. So now this vector x of t is a time-dependent function, or this tensor path can be represented by discrete samples, x of t1 and x of t2 and so on. And if the moment of inertia tensor is computed based on this function or on these samples, the notions we are going to use are theoretical value, values of this tensor of inertia. So it's lambda 1, lambda 2, and so on. And lambda 1 is the largest principal value, and lambda 6 is the smallest one. And P1, P2, P6 are the corresponding principal directions corresponding to this values. Okay, so now we can look at the particular measures. The first one is proposed by Bishop, and he, first of all, what he does, he computes the mean value of his standard path and subtracts it from the tangent path. Now he provides an integral formulation for his components of the moment of inertia tensor, and this integral formulation can also be used to provide a formulation for discrete values. So basically, each pair of components is multiplied, and then it's multiplied by y prime. So by the derivative, it's in order to take the lengths of the tensor path into account. And what he does next, he defines two measures. He multiplies, he takes the maximum of the projection of the whole tensor path only the first principal direction of the moment of inertia tensor. And he divides it by the maximum of the projections on all other principal directions. This is the first measure. The second measure looks much more simple. It's basically the relation of the two highest principal values, the square root of it. The third measure was proposed by Gaia. It's a discrete formulation, and those are the formulas for the components of the stress tensor. In his formulation, he defines his measure of non-proportionality and the ratio of the two smallest principal values of the moment of inertia tensor. Now we just look at some examples and pictures, because it's probably hard to get that much from the formulas. So basically, this is the space that's plain tensor path, so only three components are provided: sigma x, sigma y, and tau xy. And the path of this kind would be a proportional path, and all three measures would yield 0, or a value which is close to 0. This graph is a little bit different, so it's essentially very similar, but it has some strange peak looking in some other direction. And in this case, the value m1, so this one with the projections, would yield something which much higher than 1. The two other values would be still close to 0. So that's the question if the path of this kind, is really non-proportional, and if the peaks of this kind are to be taken into account during the fatigue life equation. And now the tensor path of this kind is largely non-proportional, so it goes in all possible directions, and we imagine that it's like covered by a circle, and all the measures, all these relations are near 1. So that's how these three measures work. Good. Now, another measure is based on the notion of the correlation. So what we do, we basically take two components of the stress tensor, sigma x and tau xy, and compute the correlation square. And we look through all the positions of the coordinate systems and integrate. And we do so the position of the coordinate system is given by three angles, and we integrate over two of them and minimize over the third one. So this value gives somewhere between 1, it's in kind of reference coordinate system, and so on. It can be also computed efficiently for different kinds of loadings and also for simple loadings. Now some pictures as well. So basically what this correlation does, if we have two cosine signals, the correlation between them, the cosine of the phase shift. So somehow this measure is the average of the phase shifts between sigma and tau components over all coordinate systems. And the value 1 is obtained if the principal stress are fixed, and the more circle is rotating in each direction. So it's basically constant, so these values do not change, but it's rotating all the time. So each plane experiences the same shear stress amplitude, in other words. And this would be one for this non-proportional integration. Okay. Now we can come to the measures which are critical plane based. In critical plane defined as a plane with the maximum shear stress amplitude in this case. And the factor of Heinz-Hammersala says, okay, we divide shear stress amplitude into the plane which is inclined, which has an inclination of 45 degrees to the critical one, by the shear stress amplitude in the critical plane. And pretty sure the thing leaves between 0 and 1. Okay, that works of course for plane stress conditions only. For general stresses, we can minimize, for instance, all planes which have an inclination of 45 degrees to the critical plane. Okay. And the other one is not exactly the non-proportionality measure, it's called the multi-accelerating measure, which is also critical plane based. Critical plane is also then with the maximum shear stress amplitude, and the measure is defined as the highest normal stress occurring in the critical plane divided by the shear stress amplitude occurring in the critical plane. And this value can attend each value between minus infinity and plus infinity, but modified Euler curve method imposes certain restrictions on the value, which can be actually used for particular evaluation. What I want to show are things which occur if measures of this kind, critical plane measures, are used. Okay, so we have one example. So that's the specimen. It's a welded specimen made of aluminum. It's loaded with torsion combined with axial loading. So that's those are the components. So there's the torsion and the axial loading. And if we take a look at two loads which are pretty close to each other, so we have the component, the amplitude of the sigma. So we compute based on this global loading to compute the local stresses on the ground, using a no stress concept and so on. That's not important at this point. What we have the locally this sigma x amplitude equal to 54 times the amplitude of the force amplitude. And then we have tau xy, which is equal to which is also proportional to the force amplitude. And the other loading has just a slight modification. Instead of the factor 44 or 54, we have the factor 55. And what happens if this evaluation is performed, the position of the critical plane is quite different. So in this case, it's basically not rotated at all. And in this case, it's rotated by 45 degrees. This one. And by 90 degrees in the other direction. And what we get the factor O equal to 1.97 in the first case and equal to 1 in the second case. And this results in quite different evaluation, non-proportionality evaluation, and especially quite different particular evaluation for these two loads which are pretty close by each other. So the question which arises is actually should normal stresses be considered as the critical plane is determined. Now I come to the part with the questions concerning all this stuff. So the first one is naive one, which one is better, which one makes more sense, which one can or must be used. How can such a thing be calibrated in a sensible way? Can the critical plane-based measures work reliably because of the problem which I've outlined? And the third one, if they should work reliably, should the normal stresses be considered in some way? So with that, thanks for your attention.
So I think I have answers to a few questions. I think the Kanazawa method is not going to work because